everybody, great to see you, great to see you. Ah, hello. I call these lessons, they're not really lessons, are they? If you've ever done a lesson in anything, you learn something and then you practice it for about 45 minutes and then you do a summary. That is not what we do at all. We just choose a topic, today's gravity, and we just dig right in. If you don't understand any of it, it's totally fine. The idea is that we just plant a seed in your brain that says science is amazing and the world is big and awesome and learning about it is cool. I'm going to teach you all the gravity stuff that you would learn at primary school, and then you're going to come to secondary school with me and we'll learn a bit more about gravity, and then you're going to go to sixth form and I'll tell you what you would learn about gravity at sixth form, and then we'll even go to university, and then I'll tell you some cool facts about gravity that you could learn when you're in your 30s, say. Alright, so start off, we've got to go to primary school. I'm not dressed for primary school, am I? Wait a second. Hi everyone, have you got your colouring in homework? That's right, just leave it on the table. Put your coats on your peg. Yep. Find your picture. Hello everybody, welcome to primary school. Today we are learning about gravity. Now some of you might already know that gravity is a force that pulls us down to Earth. You don't think about it, but the reason we're not floating around is because of a force called gravity. And there's an animal called a peregrine falcon which uses gravity to be the fastest creature on planet Earth. The cheetah is the fastest land animal, but a peregrine falcon flies hundreds of metres into the sky, basically just points itself downwards, tucks its wings in so it's very streamlined, and lets gravity just pull it towards Earth. Peregrine falcons, it's cheating if you ask me. But anyway, a person called Isaac Newton, you might have heard of from our rainbows lesson, he thought a lot about gravity. He came up with the idea that everything that has mass just means made of stuff, everything that is made of stuff, everything that's made of particles has gravity. So technically the Earth is attracting you, but you are attracting the Earth to you a teeny little bit. You don't have very much mass, so you don't notice your own force of gravity, but obviously the Earth is massive, it's very heavy and dense, so we're all attracted to its force of gravity. The sun, you remember from our planets lesson, the sun makes up 99% of all the stuff that is in the Milky Way galaxy, so it has a huge force of gravity, and actually all the planets go round the sun because of the force of gravity. Isn't that an unsatisfying fact? That's what you learn at primary school. The planets go around the sun because of gravity. We'll learn a bit more about that later. Now, are you ready to graduate primary school? Okay, I've got a little question for you. It's a 2-mark question. Why can you jump higher on the moon than you can on Earth? That is a 2-mark question using what you've learned so far. Why could you jump higher on the moon than you could on Earth? Okay. Fiona, fantastic. There is less gravity. Fiona has our first mark. There is less gravity on the moon, so less force pulling you down to the moon, so it's easier to bounce. For the second mark, why is there less gravity on the moon? Oh, wow, what a brilliant keyword, Katherine. Less gravity because less mass. It's mass. Fantastic. So at primary school, you get 1 mark for saying the moon is smaller than the Earth, and therefore it has less gravity. Fantastic, well done. You are ready for secondary school, my favourite school. Right, come in, Lawrence, age 7, what do you mean you haven't got your science exercise book because it's the same colour as your geography book? That is no excuse. Izzy, I don't care that your art block is 3 miles away from the science block, just... You're wasting my time and your time. Right, welcome to secondary school, everybody. Now we're going to do my favourite ever demonstration. If you were 15 years old and you were coming into my lesson on gravity and the centre of mass, you would see a fork and a spoon and a mug set up in a fascinating way, if I may say so. So we're going to do that now. You might not be able to do it, and if you can't, then you're practicing failing. Failing is important. If you don't fail, you don't learn. Here's how you do my amazing centre of gravity demo, and then I'll tell you about gravity. You get a fork and a spoon, put the prongs together so that they stick together. So like bend the prongs around. Can you see it's already... I'm nervous because I'm nervous about how angry you're going to be with me. There you go, like that. See that? That's why I told you to not use your best fork and your best spoon, because you might get a little bit of a bent fork. Can you see that? That is what you're aiming to do with your fork and your spoon. I want you to take your match and put the fiery end so that it's coming away from the curve like that. And then, so glad that I can't hear you guys. Then you balance it on the side of your mug. See? Now, it makes a difference how far in your match is. So it's just all about fiddling and not getting frustrated. You might have to put your match really close. Probably better to put it right on the edge. Keely, you've done it already? All right, I'll get talking about the silence, Keely, so that you're not bored. But if you've done it, just stare at it and think about how cool it is. Right, I'm just going to hold it on that for a bit so you can see what you're doing. And I'm going to tell you about how you've been using the word weight wrong for your entire lives. If someone says to you, how much do you weigh? And you say, oh, like 60 kilograms or 90 kilograms. What you're actually talking about is your mass. So your mass is how many particles are in your body, how much stuff makes you up. And that is measured in kilograms. Weight is a force. It's a measure of how much you are being pulled towards the planet. And it has to do with your mass. So the more particles you've got in your body, the more you weigh. But it also has to do with the force of gravity. If your mass is 60 kilograms on the Earth, then your mass is 60 kilograms on the Moon. The mass is the same. But you weigh slightly less on the Moon because the force of gravity is less. Hey, look at that. It's a good view, isn't it? I'll explain that box a bit later. Did you notice anything a bit weird about that box? Yeah. So it's not a trick. There's no strings. Centre of mass. Hard to explain, actually quite easy to understand. We say that your centre of mass is the bit of your body where if all your mass was concentrated, like if you were a marble, you'd behave the same way. Another way of thinking about it is everything balances, a thing balances around its centre of mass. Without even thinking about it, if you want to balance a symmetrical object like a Tin Peak book, you put your hand in the middle, don't you? Because usually the centre of mass of a symmetrical object, something that's the same on all sides, is in the middle. The centre of mass of, like, if you had a spoon, then you wouldn't balance your finger in the middle because you'd just understand without even thinking about it that one end of the spoon is a bit heavier than the other end. So you'd probably move your finger a little bit up the other way. So what I ask my 15-year-olds is, where is the centre of mass of the fork and the spoon and the matchstick, like all together? What point is it balancing around? Ah, Izzy did it, good. And where is the centre of mass of this box? That's why this box is a cool trick, because it looks like it's symmetrical. So you think that the centre of mass is here. You think that you have to put something there in order for it to balance. But it's balancing like that. So where's the centre of mass of this box? Shall I show you? Oh, it's so simple, isn't it? It's just a brick at this end. So the centre of mass of this box, even though it looks symmetrical, is all the way over here, and that's why it balances. Now you get your second match, and you light the match. So if nothing else, just light a match with another match is a cool thing to do. It makes like a little firework trick. But then the balancing gets even more impressive. There you go. Look at this. I did it, I really did it. There, you see? And then even the most cynical 15-year-old says, what? And. The pièce de résistance, there you go. So the centre of mass of this object, after a lot of questioning, we usually get round to the fact that it's exactly here, because that's the point at which the whole thing is balanced. So sometimes the centre of mass, the centre of gravity of an object, isn't actually on the object. There. All right. Oh, that was a lot, wasn't it? Well done, well done. You ready for Physics A-Level? Yeah, let's do it. Let's go there. Hi everyone, welcome to A-Level Physics. You've chosen to be here, so I'm sure you're all being impeccably behaved and silently looking at the screen. Right, you might have heard in primary school about Isaac Newton. To explain Isaac Newton's ideas in a bit more detail, I brought you this equation. Just give a thumbs up in your house or a thumbs down. Do you think it's scary? Do you think it's fine? Do you think you could do it? Do you think you could never possibly understand it? I'm going to have a little go at explaining this to you. So this is the equation that Isaac Newton came up with to describe gravity. F is the force of gravity, and M1 and M2 are the masses of two different objects, whatever object you want. Let's say the Earth and the Moon, because we've got them here. So M1, mass of the Earth, M2, mass of the Moon. G is just a number, it's a gravitational constant. In science, maths, a constant just means a number that always stays the same. So whatever you were doing here, like sun, earth, moon, you, whatever, G would just be the same. So let's just ignore it, okay? The force of gravity is equal to the mass of something times by the mass of the other thing divided by r is the distance between them. It sounds complicated, but think of it like sweets, okay? Imagine that this number is how many sweets you've got and you're dividing them by a certain amount of people. If this number's really big, you've got loads of sweets, hooray. If this number is small, you're dividing loads of sweets between only 2 people. That's pretty cool. If this number is big and this number is big, like maybe you're sharing your sweets out with your whole class, then this number is small, so not as good. So basically, if this number is big, the force of gravity is big. That makes sense, doesn't it? If Earth is really big, then the attraction between the two things is big. And if the distance between them is big, if this number is big, this number gets smaller. So what this equation is saying is that the bigger the mass of a thing, the more gravity it has. And the further apart the things, the less gravity they feel, which is exactly what you learned at primary school. If that's freaked you out, let's relax and do some spinning, okay? Get your A4 piece of paper, fold it up, fold it up again, fold it up again, fold it up again. Someone's joking about their house being on fire, but that's like the 8th joke about your house being on fire. I don't mind, I won't be offended if you log off. Get your string, wool, thread, anything. What we're doing is we're just making something that we can tie a bit of string around so that it'll spin, okay? So fold your paper as much as you can. You've got a nice dense bit of paper, and then shoot it in your mouth the best way, and tie your knot of string, and then just tie it out. Oh, there you go, well done. Oh, look at that. It's okay, I'll improvise. It's alright, there's only 5 people watching you live. Taut the string, I'll just tie it again, simple. Alright, when you've got this, I would like you to go and stand somewhere where there is no glass or ceramic. Get your mass on a string, give it a little spin, and then if you can, if the grown-ups that might be nearby you say that it's okay and you're not near anything dangerous, let it go and see what happens. There you go. Let's do it again for luck. We like to repeat things that are messy or dangerous in theory of science. Let it go. Woo! What happens? It flies away. It flies away, and actually it flies away in a straight line, directly at the point at which you let it go. So what does this tell us? It tells us that it wanted to get away, but you're pulling it towards you, and what you're doing, without even thinking about it, is you're pulling that string just the right amount so that it doesn't fly away and it doesn't come right smashing towards you. And that's what you have to do if you launch a satellite, say the International Space Station. If you launch it with too much momentum, then it goes whee, and then it passes through Earth's gravitational field and escapes, and you've lost a very, very expensive piece of equipment. If you don't give it enough momentum, it goes whee, and it crashes. So it probably again lost a very expensive piece of equipment. So we're going to get to story time in a minute. A woman who did this a lot. Your calculations have got to be absolutely perfect to make sure that your satellite doesn't escape, it doesn't crash to the ground, it gets stuck in an orbit. And what is actually happening is that the International Space Station is falling towards the Earth, but missing every time. It's the same with the moon. And that is an answer to one of the questions that I put on the board, but we'll get to that later. Right, yeah, Erica, it is story time. It's story time. Susanna, you don't understand. I'm sorry. It doesn't really matter if you don't understand all of this, you know. We're just giving a bit of context to some of the stuff that you learn at school. It's story time, so you can relax now. We're going to learn about a woman who became very famous for doing the calculations I was just talking about. I've wanted to tell you her story for a long time. Katherine Johnson was born in 1918 in a very small town in West Virginia. Her dad was a farmer and her mum was a teacher. So, you know, nothing wrong with being a teacher, but fairly humble beginnings for Katherine. And even as a very, very young child, she says she just couldn't stop counting. She counted everything, the dishes in the cupboard, the steps up to church, even the stars in the sky. She absolutely could not wait to go to high school to take algebra and geometry. But there was a problem. In her town, African Americans could only get an education until they were 12 years old. In America, in the 20s, people thought that once an African American was 12, they should be going off to get a job. Did that put off her parents? No. Her parents rented a house in a town over 100 miles away where there was a high school for African Americans. I'll show you it on the map, look. So she lived in White Sulphur Springs, and when they had to stay there living because that was where her dad was a farmer, but every time it was a school term, they drove all the way up here to Charleston, over 100 miles to get to school. And if you don't quite understand that because it's an American map and you live in the UK, it's like me, who lives in York, having to go to school in Wales because that's the nearest place that someone says I'm allowed to get an education. Isn't that incredible? Usually in the United States you go to high school when you're 14. She went at 10 because she was just very, very good at maths. She was very keen, did a lot of practicing. Usually you graduate high school at 18. She left at 15 and she went to college where she quickly did all the maths courses that they had. Luckily for her, her teacher was an outstanding African-American mathematician, and he designed classes especially for her. Now she quotes a conversation that they had where he says, "You would make a good research mathematician. I'm going to prepare you for this career." And she said, "Well, where will I find a job?" And he said, "That will be your problem." As she predicted, she couldn't find a job. Nobody wanted to employ her, so she got a job as a teacher. Now, we mentioned this last week. World War II happened, and World War II changed a lot of things for a lot of people. For Katherine, it meant that a very important company to do with air travel called the NACA started hiring women. It didn't want its male engineers to have to waste their time doing maths, so it brought in women who had maths degrees to do the calculations, and these women were called computers. Sounds funny now, but the first computers were women who just had sort of little calculating devices and had to be incredibly good at maths. Now, Katherine's boss is another woman who deserves a mention, another African-American woman who Katherine said moved with an authority that she'd rarely seen in other black women, who were usually just asked to take servant-like jobs. Mrs. Vaughan, you could tell, was used to being in charge. Each day as she came into the office, I observed that the white male engineers really relied on her, and I thought, if she can come from a small town and be successful, I can do that too. And then, it wasn't a war exactly that happened, but it was a similar sort of thing. Something happened which made the Americans very, very nervous. The Russians launched the first ever man-made satellite into space. It was called Sputnik. And Katherine said that the engineers were extremely cross because someone else had done it first, but also America and Russia, the countries, were not friends at the time, not friends at all. And America really didn't like the idea that Russia had now got this thing that flew over America that could see what they were doing. So suddenly, aeronautics was out and space flight was in. So the NACA changed its name. You might have heard of NASA, and there was incredible pressure on the people at NASA to get a person into space. The space race had begun. Katherine worked for 16 hours a day, and she said she loved every single minute of it. She said, there wasn't one day when I didn't wake up excited to go to work. It challenged every bit of my brain. Only male scientists at the time could go to meetings about the technology behind space travel. The women were just supposed to do the maths. But Katherine Johnson really wanted to understand what was going on with the rockets, really wanted to understand the technology. So she used to ask loads and loads and loads of questions of the engineers to find out what happened in the meetings. I mean, this got really annoying. In the end, she said, look, is there actually a law against me coming into those meetings? And this is true. They had to go away and have a little think about it. And in the end, they said, no, there doesn't seem to be a law, no. So Katherine got to go to the meetings after that, and that paved the way for other women to go to the meetings. She did what we call the trajectory analysis. She worked out where the spacecraft was going to go that took the first American into space. But the real big deal, and the story which has kind of become famous for just how successful Katherine was and how much people relied on her, comes when John Glenn, who was about to become the first American to orbit space. Can you imagine the pressure on him? Imagine how terrifying that is. We don't know much about space travel, and you are about to go round the planet and you're hoping to survive. John Glenn suddenly found out that the calculations that would get him into space had been done on a digital computer, and he totally freaked out. And he said, and this is his quote, he asked his engineers to get the girl, meaning Katherine, to do the same maths as a computer had done by hand. And he said, if she says they're good, I'm ready to go. Catherine's calculations were good, so Glenn got in his spacecraft, went off into space, and really moved the space race on significantly. So that is Katherine Johnson. What an inspiration. And her parents as well. So that was story time. Do you think you're feeling calm, relaxed enough? Yeah, ready for university? Should we go to university, see what they're learning about physics? Right, let's go. You still there? Good. Being at university is in a lot of ways just like being back at primary school. Right, a little question for you. You've been relaxing, listening to a story. A little question. If you're doing astronomy at university, you might learn about exoplanets. So the planets in our solar system, Mercury, Venus, Earth, Mars, we just call those the planets. Any planet outside our solar system is called an exoplanet. There's lots of different ways you can look for them, but one of the ways you look for them is you look for a star that is wobbling. Why, if you wanted to find a planet really far away, would you look for a star that is wobbling? Someone told me yesterday in our Zoom lesson that it was because maybe the planet is going round it, and every time the planet goes round, the star dims a little bit. Sadaf, yes. So that is one way of finding a planet, but the way I'm looking for is the three amigos have said a different planet's gravity will be pulling it. Well done, exactly. Finn, well done. Yep, you've got it as well. Exactly. So remember what I said. A star has loads and loads and loads of gravity, so it pulls the planets around it. But those planets also have a little bit of gravity, and they make the star wobble. So that's absolutely true. It's called the wobble method, and that's one of the ways that scientists are finding exoplanets. One last beautiful thing to tell you at university is that everything I've told you so far, kind of a lie. We looked at how Isaac Newton discovered this idea of gravity and how it's a force and it pulls things to Earth, and he came up with this brilliant equation. Isaac Newton's equation describes how things behave in gravity really, really well. Like literally we use this equation to go to the moon and back again. So that's cool. What it doesn't do, and Isaac Newton knew this, it doesn't actually explain like why gravity exists. It doesn't explain that at all. Now Isaac Newton was around in the 1600s, and then it was totally okay to say, well, the explanation is God wanted it to be like that. These days, scientists don't accept that as an explanation. So a chap called Einstein came up with a different idea. Now Einstein said that space and time are the same thing. He called this thing space-time. I'm going to show you, to be honest, not a terribly successful demo. If you look up a space-time experiment on YouTube after this, you'll find people who've got these beautiful big drums with lycra stretched across them. I've got an old paint bucket with some scrap fabric. But basically, Einstein said that you can imagine the universe as just being a sheet of lycra, and anything that has mass, like the sun, moon, planets, they curve space-time, okay? And then other things, everything, us, other planets, specks of dust, they all respond and behave according to the curves that are in space-time. So space-time is one thing. And we know this is true. We know this is true because, I love this blows my mind. If space and time, if space-time are the same thing, then time moves differently when force of gravity is less. So the International Space Station is really high up, it's travelling really fast. Einstein's equation says that time on the International Space Station is moving differently to time on Earth. He said that it was about 1,000th of a millionth difference, which doesn't sound like very much, but light travels super fast, so it's enough to make 10 kilometres difference every day. So every day a satellite going around the Earth moves 10 kilometres different to how we think it would, because time is moving differently on the International Space Station. Now when you get in your car and you turn on the sat-nav, what your sat-nav is doing is checking out the time difference between clocks on satellites and clocks on the Earth, and it is using Einstein's equation, because otherwise it would be wrong. Isn't that incredible? It's using the fact that time travels differently up in space to down here. So that's proof that space-time exists. Newton, he had a right idea, and we can still use his explanations to understand gravity, and you should learn them at school, but when you get further on, you learn about Einstein's ideas, and they will totally blow your mind. Congratulations. You've got your physics degree. you can go home, have a cup of tea, and just read cool books like this. Tim Peake's Ask an Astronaut. I read this in preparation for this lesson, and some of the stuff in here is totally crazy. Like, I just hadn't thought about it. Picture your life with no gravity. You probably picture yourself like upside down with all the blood rushing to your head, but the blood doesn't rush to your head in space, because in space there is no up and down. I mean, get that into your head. In space there is no up and down. Like Tim Peake says, it was really weird getting used to the fact that you could use all bits of the room. Like, there's no up, there's no down. So you could have your bed on the ceiling, like you could have your wardrobe halfway up the wall. You can use every bit of space in a room because you just float. Apparently your muscles get very relaxed, and you sort of naturally find yourself hunching and being in a sitting position, which is kind of cool. But the most amazing thing I found is why astronauts on the International Space Station float. It's not because there's no gravity. It turns out there's loads of gravity up there. It's because they're falling. It's because they're constantly falling. They're in free fall, kind of like if you're in a lift and the lift rope snaps and you fall, you haven't got anything to cling onto. It's a bit like that. The International Space Station and the astronauts in it are falling at the same speed, so they're in free fall. And how they practice on Earth for going up into space is they get in a jet plane that climbs at 45 degrees, and they've got 20 seconds as the plane tips over just before it starts going down again. 20 seconds of being in free fall, of being weightless, they call it. This plane is called the Vomit Comet because apparently it is not a cool feeling. And they do that just for like 3 hours at a time, and they've got these 20 seconds to practice being weightless. How nuts is that? Alright, oh, it's EH5, you're watching for the first time, brilliant. Okay, I've got another little question for you about the coolness of being an astronaut in space, and then we'll finish. What do you think is the grossest thing about being in space? Take your shoes off, you'll see this. You've got loads of dry, dead skin on your feet to protect your feet from when you walk. But in space you don't do any walking. So apparently after a few weeks, all the dead skin on your feet starts lifting off, and you've got to be really careful when you take your socks off, because otherwise you're just surrounded by like dead, flaky skin that floats everywhere, and the other astronauts get very upset with you. And the bit of your body that hurts the most is the top of your foot. It gets all like scaly and lizardy because you're constantly hooking your feet under things to stop yourself flying away. So there you go. I think that is my last cool fact that me, as a person in my 30s, wanted to share with you. I hope that you've enjoyed your physics journey. At the end of all my lessons, I always say thank you so much for liking my Facebook page, and thank you so much for subscribing to my YouTube channel. If you really enjoyed that and you want to support me, you can go to my Patreon page and you get like different little thank yous. So £5 and more, you get access to a magazine that I'm writing that's got a lot of competitions in it, a lot of cool information, and all my patrons get access to the activity sheet that I do after most of the lessons. So there's quite a nice gravity activity sheet waiting for you on my Patreon page if you want to sign up. I will say a very big bye. Thank you so much for coming, everyone, and I'll see you next week. And then I'll stay around a little bit and just talk to you. Ollie age 11, you can have a shout out. Oh, Anna, yeah, there's a cookbook. Thank you. Anna, what would I do without you? Everyone who signs up to my Patreon page gets access to my cookbook, which I've written, which I'm very proud of. Sarah, you're 10. Wow, you're just typing on your own, age 10. That's yeah, probably like, yeah, I've been typing for years. Seems amazing to me that you're just here on your own. Joshua, age 8, it was your first time. That's great. Lucy Slater, just the name there. Matt, age 11, you're very welcome. How do people eat in space? Yeah, good point. It turns out that you don't need gravity to eat. Isn't that weird? Tim Peake actually recommends you try that by eating a banana upside down. I don't think that sounds like a great idea, but you know, who am I to argue with Tim Peake? Zachariah, we will do plants. Yeah, plants are amazing. Photosynthesis blows my mind. Like photons of light, like particles of light hitting leaves and knocking bits of particles apart. It's insane. You burned your favourite mug. Alison, I don't know what to tell you. Joe from Manchester. Is that all you've got to say? I assume you didn't hate it because you're still here. We've been here for like an hour, so thanks, Joe from Manchester, I guess. Alright, I'm going to go on that note. Go and like my Facebook page and subscribe to my YouTube channel and watch all my previous videos, and then go on Patreon and support me monetarily. You'd have to do that. It'd be lovely to see you all. Thank you so much for coming. I'll see you next week. Bye!